Teng from Berkeley, sharing his some of his recent work with us. And I actually know Sangli for a long time. Couldn't remember how many years, but he worked with many at Michigan, and before he moved to Berkeley for the postdoc. Um, and he has a lot of exciting work on the geometric focused topics. And today he will talk more about the geometric foundation of trustworthy autonomy. That sounds a very interesting topic. So yeah, thanks to Sally giving this seminar. So we can start from here. Yeah.
Yeah, first I would like to thank Professor Zhao for this great introduction. And it is my great honor to present my work towards the geometric foundation of trustworthy autonomy. Nowadays, we can see a lot of cool robotics demos, such as the Sunday robotics for us to working on the day-to-day task, and the physical intelligence that helps people to make some coffees, and also the cool unitary demos for some martial arts in this year's Spring Festival Gala. The robotics demos today are so cool, but we know that all this method, from my perspective, is trying to overfit the data, which is true if you have all the data. But what is left for the real trustworthy autonomies and true physical intelligence? The first challenges from my perspective is that deploying the autonomous system in a challenging open world require us that our models should extrapolate beyond the training data. And although the universal approximation theory of a neural network has been a keystone for the current autonomous systems, and especially for data-driven ones, we know that there are some structures that cannot be uh, approximated. And a simple case is that uh, this universal approximation theory only works for the contact domains. And if your data or the testing data are just out of distribution, there is no mathematical guarantees and you can extrapolate to that scenarios. One example is the rotation equivalence, such that when the basic thing in computer vision is that if you rotate the picture a little bit, you also want your features to rotate a little bit so that you can still recognize the features. But if the neural network structures do data augmentation that requires we rotate the data for thousands of times, but that is not what humans or other creatures do in their brains. And here's one simple techniques to solve this problem is to directly encode these equivalent structures in the network that can enable the networks to recognize the pictures after only see it once. And the takeaway here is that geometry structures will introduce some kind of symmetries that will enable the generalizations beyond the training distributions that cannot be handled by this universal approximation series. And the second challenge is that the embodied intelligence requires real-time optimizations on the limited resources. One question is that can the autonomous system make decisions as efficient as humans? There are many great robotics platforms that can do very complicated decision makings, but we see that even for a JSON orient, it still consumes more powers than human brains. From the algorithmic point of view, instead of doing optimizations in a space that makes optimization very complicated, why not work it in a space that makes optimization more efficient? One example is a low rank optimization, such that if we know the data evolves in some low rank matrix, we can save the computing resources by constraining our space to two vectors instead of our dense matrix, so that the matrix only has rank one. And this also stems from a geometry that tells us that a geometry will enable, say, optimization in better coordinates that will finally improve the computational efficiency that enables us to make our autonomous system more efficient. And lastly, the public trust and regulatory accountability is also key challenges. Though the scaling laws has demonstrated its power in large language models of physical intelligence, we know that more data parameters may also result in a super complicated system that is hard to analyze or understand. So beyond the chasing the scaling curves, we should explore the structures in data that enforce and then enforce the structures so we wish to ensure a system can be trusted by humans. one of the structures that geometry tells us is the invariance. The invariance means that some structure that remains unchanged after transformations, and that's something that humans can understand behind the data scales or varying textures. So my research variant is that the geometry will enable certifiable performance guarantee and deeper understanding for autonomous systems. And today I will introduce my research that follows this philosophies. So in this work, in today's presentations, I'll present four of my recent work. The first one is about Riemannian interior point optimizers for rigid bodies optimizations. And the second work is about globally optimal motion plannings for rigid bodies that not only solve this rigid body motion planning problems with some optimalities, but also guarantee to obtain some trivial lower bounds for the optimization problems. And the next one is the similar global optimization framework for nonlinear Bayesian filterings. And I'll also talk about my recent work for learning the hybrid system for using some geometric method. And I will start with the first part, the geometry for physically consistent optimizations about the use that applies the interior point method, Riemannian interior point method for optimizations on manifolds. So optimizing rigid body motion is in 3D space is a very basic problem in robotics. Here we have the kinematics of a rigid body transformations that evolves on a 3x3 matrix. Here the spatial orthogonal group is a 3x3 matrix that has determinant equals to 1, and each column and rows are also normal to each others. And on the right-hand side is a homogeneous matrix that tells us the time derivatives of a rotation matrix as well as translations. If we equip it with a quadratic kinetic energy and apply the minimal action principles, we will have the dynamics that is a nonlinear equation of motions on a non-Euclidean space. Here we have the dynamics of the twist, which tell us the acceleration of the rigid body rotations and the translations on given some external force u. We know that this is a nonlinear dynamics on a non-Euclidean space that is the sources of the computational difficulties for many robotics problems. And despite that the rotation motion is very smooth, we know that here are some facts from differential topology that tell us that if we do not parameterize this smooth motions well, we have some undesired effect. Here, one of them is the fact that the spatial orthogonal group cannot be differentiably embedded into R3s. One example is the Euler angles. If we have a pitch angle equals to 90 degrees or minus 90 degrees, here will be a singularity. It's called a gimbal lock that when the robot's pitch angle is 90, they will lose 1 degree of freedom using this kind of parameterizations. Another example is the Rodriguez formulas, and when the angle equals to pi, there will be infinitely many possible changes at that point. That means the problem is generally degenerate. And also we may have some problems if we try to reparameterize the quaternions by 3 numbers. So the fact here is that although the rotation motion is 3 degrees of freedom, using 3 numbers to parameterize it will give us some problems. To avoid these issues, the only possible way is to use the over-parameterization, such as quaternions or matrix D group, to use more than 3 numbers to represent the rotations. So now we can use a very simple examples to show why this worked and how it will benefit the optimizations. Here is a very simple problem that tries to align 2 axes by a rotation matrix. The solution here is the R equals to the identities. But if we use rotations around the local x-axis and the y-axis to parameterize the rotation matrix, it will yield a very complicated optimization landscape that we have many local minimum and some saddle points. But instead, if we try to parameterize it on matrix D group, we find that the decision making, the space for decision making will be just a sphere that yields only 1 global optimum, and there will be only 1 saddle point, and this will be a much nicer space for compared to the Euler angles. And another example is a differential flatness-based motion plannings for drone. In this case, we find that when the pitch angle is equals to 90 degrees, even using differential flatness, we will have a abrupt change of the velocities if we do not properly uh, parameterize at that point. In general, given these difficulties in rigid body motion parameterizations, if we have a nonlinear model predictive controls for rigid bodies, we must properly deal with the parameterization of the rotation matrix. So in this work, I will introduce a Riemannian optimization framework that tells us how to parameterize the rotation matrix and solve this nonlinear model predictive control problems. So the first step toward this goal is to derive a singularity-free parameterizations for rigid bodies. Here we directly uses the rotation matrix as our decision variables, where the R denotes a pulse and the F denotes a pulse change. Here, all of them are using line numbers to parameterize this rotation matrix. And after that, we re-derive the equation of motions for a single rigid body in a discrete time, such that we have to first approximate the rigid body, the kinetic energies by the finite difference of the rotation matrix to approximate the time derivatives. And here we know that if we directly use the continuous time angular velocities, we will still have this Rodriguez formula. So here we use a finite difference of the rotation matrix to approximate it. And this will yield us the polynomial and matrix form dynamics that is called league variational integrators. And in this case, we find that it will preserve the energy and everything remains on a manifold. And given these parameterizations, the dynamics of the rigid body will not have singularities and still have a very good long-term energy preservation properties. And after we have this dynamics, and the next step towards this to solve this nonlinear MPC problem is to derive the solvers. Here we consider a manifold extension of the interior point solvers. Here we firstly the first step towards this goal is that we need to do a gradient descent on a manifold. On a manifold, we have to do the gradient descent only in the tangent space because we cannot go outside of the manifolds. Everything should happen in the tangent space. And then after we do tangents, go along this tangent space, we still go out of the manifold, but we can map it back to the manifold via this retraction matrix that we denoted with Rx. And on matrix Lie groups, the retraction is as simple as the Lie group exponentials. So in Lie groups, everything about the retractions, we have the closed form solutions. And the next step is to mimic what we have done in the interior point method to search the directions by the Newton steps. So on the matrix Lie groups, the optimization is done by the tile expansion of this retraction matrix and use it to expand this any functions that we want to differentiate. And if we extract the gradients and the Hessians, we can directly apply to search the KKT points using the log barrier or the log barrier problems, and which is a mimic of the classical interior point method. Now we can show some results of this, why this method, how this method competes the conventional method derived in the Euclidean space. Here we see that the first line is our proposed method. Our proposed method. For our proposed method, we consider straight line initializations for the joint landing problems. For the joint landing problems, we wish the joint to land to the identity poles starting from any initial angles. And we do the manifold interpolations to initialize it. We see that our method can converge in most of the cases with less time in each iterations. Well, for IPOpt and SNOPT, that's using extrinsic parameterizations using quaternions, we have a much lower convergence rate, even using this very good initialization, such as SDPs or other methods. And the latest, we can say that our method uses a line search, and if we apply it with some inertial corrections, we can further improve the performance, such that for a whole body control for quadrators that tries to recover from 90 degrees inclination angles, if we sample some random poses and positions, we have a 100% convergence in our testing benchmark. And that will correspond to 50 to 100 hertz cold start with a cold start. And if we consider quaternion-based parameterizations, most of the cases will trigger infeasibility restorations. That means the province will consume more power, computing resources to recover from the infeasibility province. And now we have some very initial results about a joint to do a backflipping on a joint. Here we will first make the joint to flip 180 degrees in the roll angles, and when we'll trigger the end pieces to recovers. And here we have a know that this method will converge to the tolerance for 90% of time, and that's not seen in the conventional Euclidean space solvers. Does anyone have question about this work?
Yeah, Sally, I think this is nice. I'm just trying to understand when you say the convergence, you say 100%, but this is still like a nonlinear program, right?
Yeah, right. So here
So you are
here
saying the manifold idea can kind of guarantee the convergence 100%?
I think it's the empirical findings. It's not a
Okay, okay.
theorem. Yeah,
Yeah,
so
okay.
we just say that empirically the manifold optimization landscape is much more friendly than some than some Euclidean parameterizations. Yeah, there's still
Mhm,
an empirical result, not a theorem to show
mhm,
it's
okay.
convex.
Okay. And why maybe I didn't uh follow well why this compared to the baseline approach why this your approach converge faster is this manifold constraints play an important role? Yeah,
Oh
yeah.
yeah.
Go back to this tip.
So for this IP opt and snort case, we are using a quaternions with four numbers to represent the systems, but it's over parameterizations, and we must add a manifold constraints to ensure it will not go outside of the manifold. So this manifold constraints will make the problems much harder to solve.
Hmm.
So that's why this baseline do not perform well. But yeah, I think that's the main difference compared my method and the baseline.
Okay.
It's also an empirical findings such that if we directly do everything intrinsic on manifold, it will be a better choice.
Sounds good. Yep.
After the first work, we have shown that actually we can derive the very good nonlinear optimization solvers to solve this nonlinear model predictive control problems. But another question still arise that how can we guarantee that the system converges to some global optimal solutions or globally feasible solutions? And here I proposed another method to solve this problem using convex optimization that has some degrees of guarantees. So the limitations of any local solver, for example, for this nonlinear model predictive control is that how can we guarantee the solution is globally optimal? And if it is not globally optimal, what is the optimality gap? And is it possible that the problems always remain feasible or not? All these questions cannot be answered by the local solvers, and that will be a problem for the nonlinear model predictive controls for proof of the feasibility and the stabilities. The implicit assumptions for all the NMPC convergence is that the solver should be good enough to provide feasible solutions or at least return suboptimal solutions. But this is not always true for non-convex optimizations. One example is the very weird landscape that we showed before. Here are many saddle points, there are many local minimums, and that will not be aware by these local solvers. And the due to this landscape, due to this problems, the solution quality of this local solvers will highly dependent on the optimization landscape as well as how you initialize your problems. Well, on the contrary, the global optimizations will answer the questions such that it will provide us if the feasibility and optimality is held on an entire state space. In our case, we are trying to answer two questions: that if the feasible set is empty, or if the KKD point is also globally optimal for this nonlinear model predictive control problems. One of the very popular global optimization method is the mixed integer programming that integer programs. But for some robotics motion planning, especially for the case with for the case with continuous state space and action space, we have to know that it must partition the state space for this manifold constraints to ensure it can be transformed to some mixed integer programming formulations. And in the worst case, exponentially hard, and it only works for discrete variables. Well, for our method, we know that for Lie groups, everything here should be continuous. So this method will introduce some discretization errors for the state space. On the other hand, the other kind of a global optimization method is a polynomial optimizations that don't have these problems. So here we consider a case with only equality constraints, such that we want to minimize a function f that is the cost, and the gx equals to 0 is the equality constraints. And if we transform it to a polynomial basis, we find that the cost function can be cast as a linear combination of the basis from a moment matrix. Here we have examples for r equals to 2. That means the moment matrix has degree 2, and for each columns, and it will, for the first columns, it will has a largest degree as 2. And here for the constraints, it also can also be written as a same form, such as the linear combination of the moment matrix has to equal to zeros. And then we can relax the problems by assuming that the MR is greater than is positive definite. And given this relaxations, we have to derive more constraints to ensure we have a tighter relaxations, such that for any gx equals to zeros, if you multiply it with another polynomials or monomials, it should also be equal to zeros. So we can derive this kind of equality constraints in the relaxed space. And another kind of relaxed constraint is that there are multiple identical elements in this moment matrix, so we must constrain them to be identicals. So given these relaxations, we find that if we increase the relaxation degrees r, we will have more constraints in this optimization problems, and that will yield the tighter relaxations that enable us to asymptotically approximate the original solutions. However, we know that for this moment matrix, if we increase its r, we find that this matrix will grow exponentially, will go very quickly, and that will be not going to be scalable. So to further improve the scalabilities and apply this polynomial optimizations, we must leverage the problem structure, such as the temporal sparsity for Markov chains. For Markov chains, if we have problems that, for example, the time series of action and the state, we know that the dynamics constraints will ensure that the only state and action in the consecutive time steps will appear in the same matrix, in the same constraints. So in this case, this theorem tells us that we, instead of optimizing over an entire state space, we can just use this block diagonal elements of the dense matrix for ISL decision variables that will make the problems more scalable. So to solve our previous motion planning problems, we find that actually if we have a matrix Lie group dynamics derived in this using this variational integrators, we find that everything here will be polynomials. And since this is optimal control problems, we will have this temporal sparsity as a Markov chain. So the entire problems can be solved by sparse moment relaxations or the polynomial optimizations that will be a scalable way for us to obtain the globally optimal solution. So we tested our algorithm on inverse kinematic problems that have analytical solutions for our verifications. Here we consider this 6 degrees for freedom manipulators and random samples the poses in the state space, and we may have fitable poses and infitable poses, and we find that applying this sparse moment relaxations, all the infitability point can be detected, and 90%, more than 98% of the fitable poses can be recovered by the convex optimizations. And we find that here only fourth order polynomials is sufficient for us to detect all this, to gain all these results. And if we tested it with some redundant manipulators, and we'll find that it will scale linearly because we only use this the block diagonal part of the large moment matrix that makes it more scalable. And later, we can also try this method on the joint landing problems we introduced before. We find that if we want to land a joint with a large pitch initial angles to the origins, we find that our method will yield a very small large gaps, which is almost zero for the pitch angles more than 180 degrees, and also a 2% relaxation gap for the theta equals to 180 degrees. And that's and almost surely tell us that the refined solutions by the nonlinear programming is globally optimal. The latest, we can try this problems for some more multi-rigid body case, such as a joint with a payload. We find that in this case, it has a much larger relaxation gap. For example, it's 70%. But we find that the refined solutions by the nonlinear optimizations and the SDP-based solutions are still very close to each others, which suggesting that the relaxation is not quite large. It's not. It's still acceptable. And also we can say find this method work for some very highly nonlinear systems, such as a car pose. For car pose, the gaps varies based on the initial conditions. For example, where the initial poses of the where the initial position of the pole is. We find that for very small angles, it is less than 10%, but when we have a very large initial angles for the pole to start, we have a much larger gap. We can also try this method on the quaternions-based formulations for joint. We find that for quaternion-based case, even the first order relaxations, that means it's a short relaxation works, and give us a very good relaxation gap. So we find that for solving this problem, it only yields about 5 seconds, which is much scalable than the previous method that may take hundreds of seconds to solve the problem. So the takeaway of this line of research is that if we have a Lie group-based rigid body models, it is also polynomials, and these polynomial models will enable us to convert the entire problems to convex optimization that empirically give us globally optimal solutions or infallibility detections. And that's not achievable by using some local solvers. Does anyone have questions about this work?
Can I ask one question?
Yeah, sure.
So you're saying this method can give like a convex relaxation for pretty good convex relaxations, and also infeasibility like certificate. So how do you use convex relaxation to show it's infeasible?
Oh yeah, for this problems, we find that this is the convex optimization. So the first one is a MR should be a positive semi-independent matrix, so it's a convex constraints, and the other constraints are also linear, so it's a convex. And for convex optimizations, we can actually the solver can tell the infallibility by the dual solutions. If the dual solutions goes to infinity, then the primal problem is infallible. So that's how the solvers will tell you. For convex optimizations, they see the guaranteed performance. So yeah, but for these problems, if the convex for infallibilities for these problems, if the convex optimization is infallible, then the original problem is also infallible, because this is a relaxed problem, so the fitable set will be larger. If the problems with larger fitable set is infallible, then the original problems will also be infallables.
So like if this problem is feasible, do you guarantee that there's a feasible like I don't know exactly what this problem is like feasible mixed integer result?
For this,
so the other way, like if your relaxation is feasible, do you guarantee that the original problem is feasible? I would say.
Oh no, because this is relaxed problems, but it will only provide us a lower bound for the original problems.
Yeah. Okay, that makes sense.
Yeah. So this is the empirical result, but I think future work is to prove if the relaxed problem and the original problems are equivalent. But I think it's still a very hard question to solve. But I'm very curious about the argument.
Hey, Sangli, I had a follow-up question on this. So do you choose the size of matrix M ahead of time? Do you construct that for a particular dynamical system?
As long as we can write the decision as the objective function and the constraint G as polynomials, then we can convert it to this form.
Yes, that's correct. So, but what I'm saying is, for example, if we try to do this for quadrotor,
Yeah.
do we what is the of M for a quadrotor for like 13 states or like based on the representation?
Oh yeah, I think for this method, it's highly dependent on the how do you formulate the dynamics. So our finding is that if you formulate using some polynomial forms, and that requires variational integrators, as we showed before, we can achieve this performance. So the takeaway here is that the modeling and the optimizations are highly decoupled, and certain kind of modelings will make the optimization less suffers. Yeah, so here we find that the key here is to model the problems on matrix legal for polynomial that have polynomial constraints that will make the problems easier to solve than other kind of
I see.
parameterizations. Yeah.
Yeah, just so that I understand this a bit better. So your variational integrators are what making the rotational, like the dynamics on the rotational matrix space polynomial?
Yes, exactly.
I see. Okay, great. Thanks.
Good to see you here, Yash.
Yeah, thanks for making this happen. Fun.
Yeah. After this control problems, actually there's a dual problems for the
Sangli, I think there's one question in the chat.
Oh,
I can
okay.
read it if you want.
Oh yeah, sure.
Do you elaborate on how is the relaxation gap measured?
Oh yeah, sure. Do you mean this relaxation gap? Yeah.
Yeah.
For the SDP is relaxation. So SDP will be relaxed problems. So if the feasible set increases, it will provide us a lower bound of the cost. And the local nonlinear solvers will provide us an upper bound of the optimal solutions, because everything provided by the IP-opt or the remaining optimization solvers will only be a local minimum. So if we compare the discrepancy between the upper bound and the lower bound, we have the gap. For example, the Zhou NLP here will be strictly larger than the SDP solutions. So if they are very close, that means the gap is small. If the gap is large, if the discrepancy is large, it means the gap is very large, and that will be a measures for us to say how close our solution is to the true global minimum. Yeah.
So it compares the cost function values, or does it compare the feasible set volume? Like,
Yeah, it should be compare the solutions for the problem on the right hand side and the left hand side. It's only about the cost function. Yeah.
okay, got it.
Actually,
Thanks.
I have a follow-up question. So do you actually prove that this formulation is tighter than the baseline formulation?
For this method, I don't think there is a baseline that make it work, because if we don't use this geometry-based discretizations, in many cases, it can even not be transformed to polynomial optimizations that we cannot solve it by SDPs or the mixed integer programming. So here I did not prove it's tight. It's empirically tight. For the tightness proof, there are some techniques in the perception problems, but for control problems, that techniques cannot be applied. And I'm not aware of any meaningful way of solving to prove these problems yet, but I'm happy to explore it in the future work.
Okay.
Also, I think it's an empirical result. If no more question about this work, I will move to the other one. Yeah, so in the next work, we extend the similar convex optimization framework to this nonlinear filtering problems for system with arbitrary noise, still for polynomial systems. The Kalman filter is a very famous method for linear system, such that if we know the system is linear and corrupted by Gaussian noise, we can have guaranteed optimal solutions for the minimal variance estimations. However, if we actually we can also model the Kalman filter as a Bayesian filters under linear Gaussian noise, such as we have the predictions and the update using the standard notations in the Bayes filters. However, we know that if we move it for nonlinear filtering, such that if the system dynamics is nonlinear, or if the noise and for the process and measurement models are non-Gaussians, there is actually no guaranteed optimalities. For example, for the EKF and the UKF, there is no optimality guarantees because they are generally doing some kind of approximations that do not has merely saying any guarantees on the how they approximate the true problems. However, we know that for a lot of robotic problems, especially for 3D perception in robotics, Lie group kinematics and optimizations are the key to solve the problems. And for all those Lie group poles for rotation and the translations, they have these natural polynomial structures. And we'll find that these structures will help us to deal with the globally optimality and approximation problems for the non-Gaussian, nonlinear non-Gaussian filtering problems. So here we propose the max entropy moment Kalman filters for polynomial system corrupted by arbitrary noise. So here the key step towards this goal is to prediction of the belief. So for the prediction of the belief, we find that in Bayesian filters, actually the marginalization is very difficult because we can, for arbitrary functions, we cannot obtain these solutions by analytical solutions, and that only works for Gaussian distributions. And instead of predict the belief, we find that predicting the moment is much more easy. The key here is that if we have a polynomial or the matrix Lie group post change, we find that if we want to obtain the distribution of the post X, we find that on the right-hand side, it's a polynomial. On the left-hand side, it's also a polynomially constrained manifold. So if we vectorize the entire equations and take the expectations on both sides, we find that actually this is the linear dynamical system of the moments. The moments here means not only the mean covariance, but also the mean values of higher order terms of our variables. So instead of doing these marginalizations, we will predict the moments and then try to recover the distributions. So the question here is that how can we recover the belief from the moments? And we find that if we have a distribution that is constrained by the covariance or means, there will be infinitely many distributions. But actually, the Gaussian distribution is the one with the largest entropy. That means it has the least assumptions on how the distribution should look like. So in this work, we consider this max entropy principles to derive the to recover the moments. Here we consider to maximize the entropy of the distribution while subjected to the moment constraints. And this will yield the convex optimizations that will enable us to solve these problems. Given this max entropy moment formulations, we find that on a compact domains such as the bounded states, we will have a Hausdorff moment problems. The Hausdorff moment means that given the moment constraints and everything the support is compact. And if we increase the moment orders, we can ensure that this max entropy distributions will converge to the true distributions in one norm. That means the more moments we applied to approximate the distributions, the more close we can achieve the approximate the true distributions. And this will be this will make our linear propagation meaningful because we can finally obtain the true distributions. So given this convex optimization problems, we can derive the max entropy moment Kalman filters. The first step is predictions. The prediction will rely on linear propagation moments and the regathering of the belief by convex optimizations. And after that, we have the update steps that is similar as the maximum likelihood estimations as in the MAP problems. And finally, we can recursively do this process, and this will yield recursive implementation of the filters in the classical Kalman form. And here is a numerical result of how the max entropy moment distributions will approximate some complicated belief. Here we consider a system that sampled from this very complete curve. If we use only two moments to represent the two orders of the moments to represent the belief, it will be a Gaussians. But if we increase the relaxation orders by 4, 6, and to 12, we will asymptotically approximate the true belief. And we find that as the when R equals to 12, the heat map of the approximated distribution will almost match the heat map of the samples. That means it actually goes much closer to the true distributions. And later we can apply this method to highly complicated problems for robot localizations. Here the case is that the robot has a SE2 dynamics on a plane with rotations, and we apply a range and barrier measurement such that the robot can measure one of the landmark until the positions in the body frames. But the problem here is that we may have multiple landmarks and the robot cannot distinguish them. So in a greedy association case, the robot may be in a wrong place that is shown with red arrows. It can see one of the landmark, but it will associate to another one that is wrong, that will destroy the state estimations because the robot is actually not in that space. So the optimal way is that we assign each landmark with equal probabilities. So actually, we need to deal with multi-model distributions. To deal with these multi-model distributions, the Kalman filters cannot work because it's a unimodal filters. And we applied our method to solve these problems. And we find that our method can precisely track the trajectories by treating the distribution of the landmark as a multi-model max entropy distributions. Well, for all the other unimodal distributions, the Kalman filters will fail in this case because of the greedy associations. And we can also compare our method with particle filters. Our method will perform with similar performance with 1,000 particles. The takeaway here is that not this numerically our method will have a similar result as the particle filters, but all our method implementation is based on deterministic methods. So that will make the problems more certifiable as there is no probabilistic variance in this problems. Does anyone have a question about this method?
So just maybe a quick question. When you talk about the moments, I know sometimes people go to the third moment screwness, right? And then the fourth one, I forget what it's called. But this in practice, I think you go to even like twice, order. Is that more? I think this is more like a theoretical, analysis. In practice, how much the high order ones are important.
Oh yeah. Actually, the symptotic property tells us that the more moments you have, you will go closer to the problems, to the true distributions. But in many cases, if you use many moments, the problems will be more degenerate. So it depends on what's the structures of the distributions. For example, in these structures, we find that actually when R equals to 14 to 12, we already have these patterns, and this pattern will introduce this equality constraints that constrain all the points on a curve. And if that curve appears in the moment matrix, it will actually make the Hessian matrix degenerate, and that will make the problems less stable. So I would say use as many moments as possible for a better approximation, but we have to stop before the yield condition happens. And that's when the yield condition happens, actually it's a sign to tell us that there's some patterns of the distribution is captured by this polynomial. And I think that's one of the criteria. But in series, use as many moments as possible will have a better convergence.
So there's kind of trade-off between the theoretical guarantee and the numerical performance. Yeah. Okay.
Yeah, right.
Good.
I have a question.
Yeah.
So we know that moment convergence is a weak convergence, but here you also claim that if the moment converge, you also have the TV norm of the you get the true distribution densities. I guess this is related to the assumption of compact support, I suppose. So maybe can you comment on like how realistic these assumptions will be? Because there are many cases of weak convergence does not guarantee the true convergence of you get the true distributions, right? You does not get like almost sure convergence, for example.
Yes, it's probably do not guarantee infinite norm. It's true. It's just a one norm convergence. And for compactness, I think the compactness is to ensure the problems will converge. If it's not compact, then the moment problems may have multiple limit points, and that means here will be two or more distributions with same moments, and then will not guarantee any distributions will converge to it. But I think for engineering problems, assuming a compact support is reasonable, because for noise, it is not likely that the sensors will give an unbounded input. So I think for the compactness is a reasonable assumptions. As for the convergence, I think the theories behind this method tell us it's a one norm convergence, and it does not show anything about infinity norm in the sense of infinity norm. So I think that's the argument is still constrained for compact support and a one norm convergence. It's not infinity norm. Does this answer your question?
Yeah. Thank you.
I have a question regarding the moment. So,
Yeah.
From my understanding, if you have a vector and you're taking its moments, the dimension of the moment grows. So the mean is n-dimensional. The covariance should be n square. Squareness should be n cube, I guess. So is that a correct understanding or not?
Yes. We say that if we take the like x and r, then the sorry. Can if I want to make sure if I understand your question. So do you mean if I compute the r's order moments, you want to know the covariance of the r's order moments? Is that correct?
My question is that when you're propagating the moments
Yeah.
in themselves are growing in dimension. The rth moment would be of size n raised to r. Is that
Yeah.
a correct thing to say? If that's the case, then okay. And you can still propagate them and the moments are still linear.
Yeah, right. So it depends
Okay.
on the right hand side for very specific Lie group approximation. Lie group dynamics, the right hand side will be linear. So the degrees on left hand side and the right hand side will be equal. But if we have a nonlinear equation of motion on the right hand side, then the right hand side will have a higher moments, a higher order degrees than the left hand side. So that will be a problem.
Okay. Mm-hmm.
But for this very specific robotics problems with Lie group kinematics, we have actually a linear propagations.
Okay, understood. Thank you.
Yeah, thanks. Okay, and finally, I would like to introduce my recent work about learning hybrid dynamical system. So the hybrid dynamical system can model a wide range of robotic problems, such as this robot skateboardings, such that when a robot do skateboarding task, each mode of the motions can be approximated by a continuous time dynamics and can be continuous dynamics that evolves on a state space described by this vector field. And when the state reaches the gap surface, it will be mapped to the other side of the state space by this reset functions that only happens in discrete time. We know that the hybrid system is very expressive and also very structured. That is a very ideal abstractions for complex robotic systems. However, we know that learning such a hybrid system from data is challenging, although it will, but if we can learn such a representation, it will provide us a pathway towards interpretable embodied intelligence because we want our models to be both expressive and structured. Here the problem is that we have the samples from the hybrid system trajectories and we want to accurately regard the flow of hybrid systems. Here we know that we actually have no knowledge of the modes, guards or reset functions because this system priors are very hard to infer from this time series data if no more prior is provided. There are a few challenges that makes this problem hard. The first one is that detecting and computing the gradient serial events will be hard. Say that we don't know the exact time of events in event-based simulations. And in this event-based simulations, if the problem is not initialized well, we may have some ill conditions because of problems is super sensitive to the guard surface. And if we instead want to approximate the system by a continuous neural network, the impulses and the state reset will make the problems hard to learn because for impulses, the time derivatives will be infinite. That means it cannot be captured by the neural networks with finite Lipschitz constants and bounding input and output. And lastly, if we have a system with multiple modes of dynamics, then assigning each trajectory to the modes will be exponentially hard. And that will be a combinatorial problems, and that's not quite something we should avoid. So in general, we have want to learn discontinuous systems, but we see that if we consider some geometric method, we can actually make it smooth and continuous by the series from geometry and topology. And in my research, I will show how to make this work possible. So my solutions builds on this geometric series for hybrid systems. Actually, the reset function induces equivalence relations that identifies a pre-impact state and the post-impact state as identical in a topological space. So intuitively, this equivalence relations will induce the quotient manifold. That means certain parts of the state space are identified as identicals, and that's intuitively corresponds to some kind of a gluing that's we've just fold the state space and glue it at the guard surface to make it continuous. And the existing theory suggests that the quotient manifold is a topological manifold. That means it's continuous and its boundaries are also piecewise smooth. The question here is that how can we learn such a representation from the data? And this is not answered by this theoretical papers. And my research will learn these representations from time series data using this encoder decoder structure. Then first convert the state space trajectories to the latent space and then decode this to regard the hybrid flow. The key to making this framework is to have good encoders. Here we know that encoders will be functions that glue the pre-reset state and the post-reset state as identicals. However, we know that for random function, it's possible that they collapse everything to one point because we glue 2 points, but the encoders may just glue everything to 1 point as a trivial solutions. Or it is possible that these encoders introduce self-intersection. That means 2 points that should not be glued are glued by these functions. I think in the ideal case, we want to get rid of the self-intersection or the rank degeneracies. And in my research, I find that in the differential topology, the white embedding theorems in differential topology can have these guarantees. That means if for n-dimensional manifold, it can be embedded into a 2n-dimensional space. That means if we just increase the dimensions of the encoders to be larger than twice or equal to the twice of the input dimensions, we can guarantee there will we can control the encoders to ensure there will be no self-intersections or rank degeneracies. So this is a contradiction to the computer vision that tries to compress the dimensions. But in this case, we want to preserve the topological properties. So the over-parameterization is very necessary. And in our next research, we find that actually we can also guarantee the latent vector field is also continuous. In the original state space, we find that the pre-reset state and the post-reset state are not identical, and the vector field associated are not identical. But actually, in the embedded images, we can control the degrees of freedom of the encoders to make them match. And we further proved that if the m is greater than 2n, that means the latent dimension is larger than twice of the input of the state space. We can ensure that the latent vector field match across the Gauss surface, and there will be no self-collisions or rank degeneracies. And we will skip the proof, and the paper is on my personal website. After these two existing theories, we can design algorithms to recover the hybrid system from time series data. So the first step is to encode the state to a high dimension latent space that, for example, the m is greater than 2n to ensure the latent continuity for both the vector space and the manifold. And then we can integrate the latent vector fields to obtain the latent trajectories, and then we can decode the predicted latent states to recover the flow. And if we have another inductive bias from topologies to ensure the avoid the latent collapsing or gluing, we can further improve the performance. Oh, we have to show that the key here is to key to the loss function design is the reconstruction loss and the latent consistency loss that to track both the state trajectories as well as the latent trajectories. And this method will only requires time series data, and all components are differentiable and will post. And now we can choose some baseline method. For example, the neural ODE that learns everything in the state space, and the latent ODE that have the RNN-based encoders, and the Koopman operators that learns linear dynamics for some parameters. But all of these methods will fail for very different reasons. For neural ODE, to suffer from the impulses, and the latent ODE, it lacks this topological inductive bias. And for Koopman operators, it is still very hard to control the eigenvalues if no more system prior to show the system is divergent or convergent. So lastly, we also try the neural event functions that is try to learn the Gauss surface and the reset function separately. But we find that this method will suffer from the yield conditions, as we mentioned before, because they are very sensitive to how the different components are parameterized. And we can also compare our method with the neural ODE that has a relatively good performance. We find that our method will not have penetrations and have a much smaller gap compared to the neural ODE. Where the neural ODE has larger gap and have a larger penetration, such that when the ball hits the walls, actually we find that the ball is actually inside of this wall because due to this impulses at the contact. And later, we can also plot the state trajectory of our method. We find that our method can predict this hybrid flow pretty good, despite that the system is truly very discontinuous. And we can also verify that the latent trajectory is also much smoother than in the state space, which is a continuous signals compared to the left one. And finally, we find that we can also test this method for a system with very complicated or non-trivial topology, such as a system equivalent to a torus. Say that this reset function will map in this ways, and if we glue it, it will be equivalent to a torus. And we can also try a system with the equivalent to a plane bolus, such that it can only be embeddings in a four-dimensional space. Our method can track all the trajectory well, but the other method will fail because they lack of topological inductive bias, or just because the system is super hybrid. And the more interesting thing we can do is that if we have the encoders, we can just sample the state space to obtain the latent point cloud. And this latent point cloud can be used to compute the Betti numbers by some topological analysis tools that tell us how many holes or circles are inside of this latent space. And there will be a robust descriptors for the invariance to tell us actually this is the structure that is invariant to the beta scales. So in summary, this hybrid system learning work transforms a discontinuous hybrid system to a fully differentiable geometric object. And this will be a theoretical foundation for learning hybrid system from large scale data. And the topological invariance obtained by this system will just provide us a pathway towards a more interpretable embodied intelligence. And Thank you. And that's all of my research. And if you have any questions, I'm happy to answer it.
Okay.
Um,
Thanks a
I've
lot, Sangli. Yeah, this is nice work. Yeah, go ahead.
Yeah, I
Question.
have a very general question. So, like, is your encoder only like able to learn the reset function for one type of the transition, like from one type of transition? Like, are you basically you already have a definite like modes transition? Are you able to like know like but like in a lot of cases like you don't know like which mode to try to go to. So like, could you tell like which mode this like transition function is actually, um, when
Uh,
they hit the guard, like which modes go to,
oh yeah, I think the explicitly detecting the mode and classify the trajectory segments is what we want to avoid. So in this work, we are just regarding the flow. As you see in the problems formulations, we only want to learn the flow. So just the tail initial conditions and the time we want to roll out, and then we get the state at t. So, but we don't want to obtain the guard surface and reset functions because this will introduce yield condition problems in the event-based simulation, and that's what we want to avoid. I think a nice future work is to identify this flow, identify the mode without affecting how the flow is learned. Yeah, so I think an external classifier is better choice instead of learning the guard surface and reset function inside of this roll out the trajectories, because that will make the problem super unstable.
And also like sometimes, this guard like what this like the timing of like when this transition happen also like kind of like varies. So um is your encoder can able to like learn the timing as well?
You mean the time to transition?
Yeah.
Yeah, I think uh, I think for this method, the encoder and the vector field will be continuous, but the decoder will be discontinuous because we are trying to differentiate two almost identical points to two very different points. So the decoder must be discontinuous. So I think the decoders can tell us roughly when the transition happens, but not exact. In this case, we consider a continuous neural network as a decoder, so it is still a L1 or LP approximation to the truly discontinuous decoder. Yeah, as we said before, detecting the exact time of event is hard, but we can provide approximations by the decoders in this case.
Okay.
It's only very nice presentation. I just have a question about the interior point where
Yeah,
you presented. Yeah, I think the idea is pretty interesting. Yeah, it's probably just, too many slides away, but yeah, I remember you had a lot of pretty good benchmarks, but just wondering like what's your thought on like scalability or in terms of the computational wise, and like for example like how is scaled to like much higher degrees of freedom system versus like more commonly used minimal coordinates, and you have like whole body control for a quadrilateral as well. Yeah, I just want to see some of your thoughts on how it can scale to different systems.
Yeah, I think the bottleneck of solving this problem is to search the KKT point. For the KKT point, we need to obtain a hasten. So it's mainly depends on the KKT matrix. So for compared to this, compare this work for a single rigid body, this work is a minimal coordinates because it provides intrinsic derivatives that is much smaller than the baseline methods. For the baseline methods, it's an extrinsic representation that use four number to represent the quaternions, and all the numbers needs to be optimized. So that is less efficient. But our method is intrinsic, so it's more efficient. And for the scalability to high dimensional system, I think it will be identical to the Euclidean case, because the only difference between our method and the Euclidean-based Euclidean IP-opt is the how we divide the gradients and hissings, and that will not introduce additional degrees of freedom. So I think scalability will be identical to the Euclidean case. But the difference here is that if the Euclidean case requires you to use over parameterizations, then our method will be more scalable.
I see. Makes sense.
Any more questions? Maybe Sally, I'll ask a maybe unrelated question.
Yeah.
So you are not really touching on anything on the RL.
Yeah, actually,
I
personally, I
saw
didn't.
Kush's group has a like RL paper like exploring or learning the symmetry idea a few years ago. But you are not really putting anything into the RL world.
I guess the only RA work is this one, in collaboration with Hung, a master students from Michigan. Yeah. So personally, I do not do much on learnings. Yeah, but I guess since I'm more interested in the geometric method, and I'm trying to see if the geometry or some systematic bias can help learning. I think the takeaway of this kind of like the robot skateboarding task is that we need to use a multi-critic to make it work. That means each modalities of the skill needs a separate critic networks to evaluate the values. And that's kind of an invariant pattern from the data that will help the skill learnings. We tried the vanilla PPO, but they just cannot learn such a such a diverse of modalities.
Okay.
Yeah, but personally, I did not do much work on reinforcement learning.
Remember, you have a work on word model.
Oh yeah, that's a recent work. I did not introduce in this paper, as it's already on my personal website and Hans' personal website.
Okay.
Okay, sounds good. I think there's one comment from Professor Naka. He already left, but I think he leave a comment on this assumption of a compact support. So I don't think it's a question, it's maybe just a comment. So if you want to read it, you can.
Oh yeah, just take it.
Yeah.
I don't think it's true, but yeah.
Oh yeah, I think for compact support, the assumption is to ensure the moment problem has a unique convergence.
Right.
Yeah.
Right.
So
right.
if
I think it's
convergence,
needed.
Yeah, right. If we don't have this assumption, then it may converge to another point. But
right.
in engineering perspective, yeah.
Yeah, even for like finite moments, it does not guarantee L1 convergence or unique solutions. So I think boundedness is absolutely needed.
Oh, so if it's for if it's for compact domain, non-compact domain with finites, there may also not converge.
It might not have lead to unique solutions or in L1 convergence, I believe.
Okay, yeah.
Right. And I think in general, because moments are just like a kind of a weak criteria for finding distributions, right? You either, I think the best way is to learn some kind of quantile functions, I guess. Even densities are sometimes not even ideal in this case. But yeah.
Yeah. Thanks for the comments.
Okay, all right. This is a great talk, and if no more questions, I think we can wrap up here. And let's thanks Sangli again for this nice talk. Very nice work. Yeah.
Thank everybody for attending.
Look forward to see more results,
Yeah.
Okay, good. All right. Let's stop here. See you guys.
Okay. See you.
Okay, bye.